hello there. So today we will look into chapter 11, okay, on nuclear and particle physics lah. Okay, so first let us go through with example 11.1. Okay, so this one they wanted to calculate the binding energy. Okay, binding energy of an aluminium nucleus. Okay, the properties of the particle is given. Okay, nuclear number and the proton number, okay, in MeV. Okay, so the information given over here, you have mass of neutron, okay, mass of proton, and then mass of electron, okay, and then speed of light in vacuum, and atomic mass of aluminium is given lah. Okay, so this is all the constant. Okay, so to find the binding energy, okay, so number of proton, okay, we have 13, okay, and then the atomic mass, okay, we have 27. So from here we can determine the amount of neutron available lah. Okay, so nuclear number minus with atomic number, okay, so we will end up with the number of neutron, which will be 14. Okay, so now once we have the all the value here, okay, so to calculate the mass defect lah. Okay, so we can calculate the mass defect from the mass of the nucleus lah. Okay, so mass of the nucleus will be equivalent to the mass of the aluminium. Okay, we minus with the mass of the electron lah. Okay, so consider this atom is in neutral lah. Okay, so we have a neutral atom, so that means number of proton and electron will be equal lah. Okay, so which will be 13 lah over here. Okay, so the proton and electron will be equal 13. Okay, so the mass of the electron given, so this will be the mass of the nucleus lah. Okay, so once we take the total mass of the atom and then we minus with the mass of the electron, so we end up with the total mass. Okay, and then to find the mass defect, okay, mass of the proton, okay, total mass of the proton, and then add up with the total mass of the neutron lah. Okay, and then minus with the mass of the nucleus. Okay, so over here Z, okay, proton we have 13, okay, and then neutron we have calculated, which is 14. Okay, multiply and then minus with the total mass of the nucleus. Okay, so for this calculation, okay, so whatever value that you obtain in your final answer, okay, do not round off. Okay, so just leave it how many decimal you have over here. So for example, you have 0.24146. Okay, so even though if you get 0.0001, okay, so that is your final answer. Do not round off. Okay, so for this one, just take the value, the full value, full decimal that you have obtained for the mass defect lah. Okay, so once we have the value of the mass defect, so we can use it to calculate the amount of energy lah. Okay, so the binding energy will be equivalent to mc square. So over here will be delta m, which will be the mass defect. Okay, so mass defect should be in kg lah. Okay, so the previously we calculate in atomic mass unit. Okay, here you need to convert into kg. Okay, so for the conversion, okay, delta m, so we convert first into kg. So once we obtain the answer in kg, okay, so the binding energy will be equivalent to mc square. Okay, so this one we will end up in joule. Okay, so once you obtain the answer in joule, the final answer they want you to provide in MeV. Okay, so to convert into MeV, we use the conversion ratio. Okay, so yeah, this will be the value in MeV lah. Okay, 1 MeV will be equivalent to this amount of joule. Okay, so therefore to convert, okay, divide with the value, so the final answer we will end up with MeV, so which will be equivalent to 225 MeV. Okay, so this is the first method. Okay, so that means we use SI unit. Okay, convert the mass in kg, we calculate the value in joule, and then finally we convert into EV. Or the second method, okay, what we can do is that we can use back the formula, okay. So we use the value in atomic mass unit, okay, where one atomic mass unit will be equivalent to 931.5 MeV, okay. So this one in front in notes available, okay, how we end up with this conversion. So what you can do, you can straight away replace in the value, okay. So over here you have a ratio of MeV over C square, and then at the equation you have C square, okay. So which will cancel off lah later on, okay. So the final answer, so which you end up with, okay, 225. So you should be able to get the same value lah by using these two different methods. So only thing is that this method will be much more simpler lah, okay, because it involve less conversion. Because you want your final answer in MeV, so you straight away apply this equation, so you end up with final answer in MeV lah, okay. Alright, so for 11.2, okay, example 11.2, they wanted to calculate the binding energy per nucleon, okay, of boron nucleus. So binding energy per nucleon, okay, we will follow the same method with the previous example, okay. It just once you have the binding energy, we find the per nucleon value lah, okay. That means you divide with the nucleon number, okay. So for problem solving, okay, so same method, okay. So we have proton number 5, okay, nucleon number 10. So from here we can determine the number of neutron lah, okay, which will be 5, okay. And then the mass of the atom is given, so we need to determine the mass of the nucleus. So atom minus with the amount of electron lah, okay. So for this chapter, the problem solving, we assume that all the atoms are neutral. So that means the number of electron will be over here, okay, will be equivalent to the number of proton lah, okay, which will be 5, okay. So which you end up with the mass of the nucleus, okay. And then for the mass defect, okay, amount of proton, okay, times with mass of proton, and then add up with the nuclear number of neutron, okay, mass of neutron, and then minus with the mass of the nucleus lah, okay. So which you end up with the mass defect for the nucleus, okay. So the binding energy, okay, so we just apply delta mc square, calculate the binding energy. So this one over here we use conversion lah, okay, to convert into kg, okay. So final answer we will end up in joule, okay. So for the binding energy per nucleon, okay, so we just divide by nucleon number lah, okay, so which will be 10, okay. So this will be the final answer lah, okay, binding energy per nucleon. Okay, so for example 11.3, okay, this one, why is the uranium 238 nucleus is less stable than carbon 12, okay. Give an explanation by referring to the repulsive Coulomb force and the binding energy. So this one they wanted to provide two answers lah, okay, repulsive Coulomb force and the binding energy per nucleon, okay. So all the value constant given down here, okay, you can go through with that lah, okay. So for solution, okay, first we look into repulsive Coulomb force lah, okay. So for the aspect of repulsive Coulomb force, okay, so for uranium 238, okay, we have 92 proton, whereas for the carbon, okay, we only have 6 proton lah, okay. So therefore the Coulomb force inside uranium 238 nucleus will be, okay, so 92 divided by 6, that means 15.3 times greater lah compared to the carbon, okay. So that means the Coulomb force inside which will be much more higher compared to carbon. So that means this makes the uranium to become less stable, okay. So this is one factor, okay, due to the repulsive force lah. So it becomes less stable. Okay, another one we answer based on the binding energy per nucleon. So to answer based on binding energy per nucleon, so we need to calculate the binding energy lah for both uranium and carbon nucleus. Okay, so let's look into the calculation lah. Okay, so first we do calculation for carbon. Okay, so for carbon, okay, same like the previous. Okay, calculate the mass of the nucleus first. Okay, so that means minus with the mass of the electron. Okay, so 6 proton, so that means you will have 6 electron, so which will end up with the mass of the nucleus. Okay, and then for the mass defect, okay, mass defect, total mass of proton and then total mass of neutron minus with the mass of the nucleus. Okay, so which we end up with 0.09893 U. Okay, and then to calculate the binding energy per nucleon, okay, delta mc square over A lah. Okay, so we straight away replace in. Okay, so this one we use straight away answer unit conversion in MeV lah. Okay, so final answer we end up with 7.68 MeV per nucleon. Okay, so this is for carbon lah. Okay, binding energy per nucleon for carbon. Okay, so repeat the same process for uranium. Okay, calculate first the mass of the nucleus. Okay, so once we have the mass of the nucleus, we can determine the mass defect. So once we have the mass defect, we calculate again the binding energy per nucleon. Okay, for uranium, so which we end up with 7.57. Okay, MeV per nucleon. So we compare lah. Okay, so since the binding energy of uranium 238 is less, okay, so if you look at the value is less than the binding energy of the carbon 12. Okay, and the Coulomb force inside uranium is greater than the Coulomb force of the carbon 12. Okay, therefore uranium 238 nucleus will be less stable compared to a carbon 12 nucleus lah. Okay. Okay, for example 11.4, this one we have a radioactive nuclide. Okay, A disintegrate into substance, a stable substance, nuclide B lah. Okay, and then half-life is given as 5 days, and then the initial number of nuclide, okay, is given. So they wanted to calculate the number of nuclide B after 20 days. Okay. So for the solution, okay, so the information given, okay, half-life, okay, initial number of atoms, okay, and then the time period lah, which is 20 days. Okay, so substance A disintegrate into becomes B lah, okay, and then it releases energy. Okay, so to determine the decay constant, okay, we already given with the half-life value. Okay, so apply in this equation to determine the decay constant, so which we end up with 0.139 per days. Okay, so this one whenever we do calculation, make sure the unit of the decay constant and the time period is in same unit lah. Okay, so for example if your decay constant in per year, then your time frame has to be in per year also lah. If it is in second for example, then the time frame has to be in second lah. Okay, so make sure you use the same unit lah in calculation later on. Okay, so for the number of remaining nuclei, okay, so we apply the equation, so replacing the value lah. So initial number of nuclei, okay, exponential, so decay constant times with T. Okay, so which will end up with 6.2 times 10 to the power of 18 nuclei. Okay, so the number of A nuclei that have decay will become nuclei B. Okay, so this one they wanted to calculate the number of nuclei B, right? Okay, so the one that have decayed will become B. So what we do is that we take the initial, okay, minus with the atoms which have decayed. Okay, so this will become as nuclide B lah. Okay, so the amount of nuclei B will be formed will be equivalent to the amount of the A which has decayed lah. Okay, Okay, so next let us look into example 11.5. Okay, so radiative decay is a random and spontaneous nuclear reaction. Explain the terms random and spontaneous lah. Okay, so this one you can refer to the notes lah for the explanation. Okay, B, 80% of a radioactive substance decays in 4 days. They only determine the time constant. Okay, and then the half-life of the substance. Okay, so this one explanation. Okay, so later you can just go through lah. Okay, now we look into the calculation part lah. Okay, so time 4 day, so 80% decayed, so that means remaining, so 100 minus 80, so you end up with balance which will be in 20% lah. Okay, so 20% you convert in terms of value which will be 0.2 lah. Okay, so that means 20 over 100 lah. Okay, from the initial. Okay, 20% from the initial. Okay, so this is the remaining lah. Okay, so remaining. So what we do is that we apply into the equation. Okay, radiative decay equation. So the remaining will be 20% from the initial. Okay, and then the time period given as 4 days. Okay, so if you solve this, okay, we will end up with the decay constant lah. Okay, so which will be 0.402 per day. Okay, so once we have the value of the decay constant, we can apply in to find the value of the half-life. Okay, so which you end up with 1.72 days lah. Okay. Okay, example 11.6. Phosphorus 32 is a beta emitter with a decay constant given. For a particular application, the phosphorus 32 emits, okay, 4.0 times 10 to the power of 7, okay, beta particle, okay, every second. Okay, so they wanted to determine the half-life of the phosphorus, okay, and then mass of the pure phosphorus 32, okay, given which will give this decay rate lah. Okay, so the value of the Avogadro constant given. Okay, so the value of the decay constant given. Okay, and then emits beta particle, so amount of decay lah. Okay, amount of decay per second. Okay, so given. Okay, from the decay constant we can determine the half-life. Okay, so which you end up with 1.24 times 10 to the power of 6 second. Okay, and then for the mass, okay, so by using the radioactive decay law, okay, so this is the amount of decay rate lah. Okay, dN over dt. Okay, value of the decay constant we already determined, so we can determine the number of atom. Okay, so which you end up with 7.14 times 10 to the power of 30 nuclei. Okay, so by using the Avogadro constant, okay, so if you relate lah, okay, so for, okay, 6.02, okay, times 10 to the power of 23, okay, nuclei will have a mass of 32 gram. Okay, so therefore we determine the amount of mass for the calculated value of nuclei lah. Okay, so which we end up with 3.8 times 10 to the power of negative 9 gram. Okay, so this is the amount of mass lah. Okay, for this value of the atom. Okay, so this one we just compare with the ratio from the Avogadro constant lah. Okay, example 11.7. Okay, you have a thorium 228 isotope, okay, which has a half-life of 1.913 years, okay, of decays, and then it decays by emitting alpha particle into radium lah. Okay, then it becomes a radium 224 nucleus. Okay, calculate the decay constant, and then B, mass of the thorium 228 required to decay with the activity of 12 curie, and then see the number of alpha particle per second for the decay of 15 gram lah. Okay, 15 gram of thorium. So the value of Avogadro constant is given over here. Okay, so over here the half-life is given in year. Okay, so to determine the constant, convert it into SI unit lah. Okay, so we should be in second. So the decay constant, okay, so which will end up in per second lah. Okay, and then for B, okay, so Curie we have to convert into decay per second, so use the conversion. So over here we have 12 Curie. Okay, so use the conversion, so we will get the decay in per second unit lah. Okay, decay per second. So once we have the decay per second, okay, the activity, we can calculate the number of atom lah. Okay, so the number of atom available. So we have 3.86 times 10 to the power of 19 nuclei. Okay, so once we have the amount of atom, okay, we can use the Avogadro constant and relate with the mass number, okay, molar mass, to calculate the amount of mass lah, okay, that is available for this amount of atom. Okay, so calculate the ratio, which will end up with 1.46 times 10 to the power of -2 gram. Okay, and for question C, this one they have given, okay, the mass. Okay, so from the mass, use back the ratio of the molar mass and Avogadro constant to determine the amount of nuclei lah. Okay, nuclei or atoms that is available over here. Okay, so which we calculate, we end up with 3.96 10 to the power of 22 nuclei. Okay. Okay, so based on the amount of atom that we have, okay, we can determine the activity. Okay, so that means decay per second. Okay, so we can ignore the negative sign, so we shows the decay. So decay constant multiply with the number of atom. Okay, so which we end up with the activity, which is equivalent to 4.55 times 10 to the power of 14 alpha particle per second lah. Okay. Okay, example 11.8. Okay, this one we have a iodine isotope, okay, which has a half-life of 8 days, okay, and used for the treatment of the thyroid gland cancer. A certain sample is required to have an activity of 8.0 times 10 to the power of 5 becquerel, okay, at the time it is injected to the patient. So this one they wanted to calculate the mass of the iodine 131 present in the sample to produce that required activity, okay, the mass. And then B, it takes 24 hours to deliver the sample to the hospital. What should be the initial mass of the sample? Okay, so this one we prepare before being injected lah, okay, 24 hours before. And then what is the activity of the sample after 24 hours in the body? Okay. Alright, so solution for A. Okay, so half-life given, convert into second. So activity we have in a becquerel. Okay, so this one will be the initial or referent activity lah. Okay, so the decay constant. Okay, so we can calculate based on the half-life given. Okay, so which you end up with this. Okay, 1.00 times 10 to the power of -6 per second. Okay, from the decay relationship, okay, A activity will be equivalent to -n naught. Okay, so activity is already given. Okay, the required activity, decay constant given. So we need to determine the amount of nuclide lah. Okay, or the atom that is required to produce this amount of activity. So which you end up with this nuclei. So once you have the value of the nuclei, okay, amount of nucleus, okay, use the ratio of the Avogadro constant, okay, with the molar mass, okay, to find the amount of mass required. okay, so which you end up with 1.74 times 10 to the power of negative 10 gram lah, this one. Okay, so for B, okay, bring back the initial equation given. Okay, so now this one we have a time period given 24 hours. Okay, so convert into second. Okay, so let's say after 24 hours the mass becomes as the calculated value lah, okay, which you have calculated in question A. Okay, so now we want to determine the initial mass. Okay, so this one we can use exponential law. Okay, so final mass, okay, decay constant given, time period given, determine the initial number of atoms lah, okay, or the mass. So final value which will end up with 1.90 lah, okay, times 10 to the power of negative 10 gram. Okay, and for C, okay, after 24 hours, okay, so the initial activity is already given in the question, so just apply in lah, okay. So with the time period, so the final activity we will end up with 7.34 times 10 to the power of 5 becquerel lah. Okay. Okay, for final example 11.9. So this one, an archaeology digs and finds a fragment of an ancient basket, okay, woven from grass. Okay, later it is determined that the carbon-14 content of the grass in the basket is 9.25%, okay, equal to the carbon sample present from the today lah, okay. So that means this is the remaining value lah, okay. If the half-life of the carbon is given as 5,730 years, they wanted to determine the age of the basket. Okay, so this one method we call it as carbon dating lah. Okay. So for the solution, okay, so the information given. Okay, for this one, I think you don't need to convert lah. Okay, so the half-life you just can leave it in years. So your final answer you will end up with years lah. Okay. So half-life given, so from there we can determine the decay constant. So make sure the unit is same lah. So the decay constant we use in per year. Okay. So determine the age of the basket. Okay. So this is the remaining lah. Okay, remaining. Okay, remaining from the initial. Okay, so the initial and not. Okay, decay constant times T. So from there we can determine the value of T lah. Okay. So which is 19,000, okay, 674 years. Okay, so that's all for chapter 11. Okay, so good luck for your finals lah. Okay, and wish you all the best.